Finishing up Chapter 8. In Chapter 8, we studied worlds. The worlds that we can actually get to, our hood, our solar system. Now, as humans, we can't really get there yet. But we can send spacecraft, and they'll get there in our lifetimes, in our solar system, all the stuff going around our sun. And so what we've studied are the four inner planets and how they've got the metal inside and then the rock around it and the crust and maybe it's got an atmosphere and all that stuff. And my very excellent mother, right? Actually, just sent us 9 pizzas and Coke. We've studied the four, got a sense of those gas giants, and ice giants, and what's going on with those. And now we're going to talk about some moons of interest. And moons and rings are connected. So let's go over some. We're going to go over like 12. We'll have gone over, if you include our moon, about 12 of them of the around 200 moons in our solar system. Before I do that, I want to show you this picture, and I noticed that I had not quite had not said something that I wanted to say. A couple of things, and so a nice little review, right? So the interterrestrial, we clearly don't see the distances here because you wouldn't be able to show it, but the sizes, right? We've got the iron in the middle and then the rock around it and that kind of thing. We got the size keeping these warm inside, right? Releasing gas, still active. Right? An atmosphere, nice. Very thick atmosphere, a thin atmosphere. This has about 100 times the gas that Earth does, kind of the way Earth started, perhaps. This has about 100 times less gas in its atmosphere, namely Mars. You know my very excellent mother, so you know these, and you know them fairly well. The planet of threes or a third, the planet of twos or a half. So we talked about that. And you see this size, Mercury. You can get about 3 of those across Earth, right? It's closer to the sun. This would be the size of our star, sun. It's closer to the sun, and yet still inside, it has cool because it's small. And the side that doesn't face sun, it doesn't have a blanket, so it cools rapidly, right? So it's cold inside. So if we took something the size of Mercury, or even a little smaller, size of Moon, and we put it out to the outer planets, what would you expect? We're going to talk about that. And then we've got the outer planets, right? 10 Earths across, 11 if you want to be picky. 10 Earths across, 9.5 if you want to be really picky. And I think it's kind of cool to look at the colors. So we know these have solid surfaces, maybe with some atmosphere here, none atmosphere there. But this is gas, right? And so when you study these, you've got crazy gas and layers of atmosphere and gas and then squeezed down into liquids and all kinds of interesting things. I like looking at the colors too because this is kind of, you might call that red, you might call it brown, you might call it orange, some reddish orange, something like that. And you see this yellow. Hey, wait, rainbow colors. Roy G. Biv, red, orange, yellow, green, blue, violet. Red, orange, yellow, green or greenish blue, and blue. So why the colors? The colors has to do with the chemistry. So when we study this, when we study geology, rocks, we study these kind of things. The details are in a lot of the chemistry, the temperature, the pressure, the composition, the kind of atoms, and so on. In particular, these two, I just want to mention, why are they kind of a greenish blue or blue? And that has to do with methane. So the cool thing out here is that we've got water, which is oxygen with hydrogen. H for hydrogen, H2O. They've got ammonia, which is nitrogen with hydrogen. And they've got methane, which is carbon with hydrogen, which is effectively what natural gas is, a little bit of stuff. So it's like natural gas. So you have this. And these have a lot of that methane, that carbon. Remember I talked about the diamonds a little bit? And what happens with methane is that if you shine all the colors, like white light, onto it, the reds and oranges get absorbed and the blues and greens get reflected, and that's what gives them their color. So that's a little thing. So we studied these worlds. What about moons? Again, they're so small, so small. And Where do they come from? How do you get moons? There it is. So moons can get caught. Remember that ours kind of got caught, except it hit us in the face and broke into pieces. They can be captured. And that happens some, but mostly it's co-creation. Get out of your way here. Co-creation, which you can think of as accretion, right? As the planet formed, so it's kind of like a mini solar system, like a mini chapter 7. As the planet formed, the gas bits around it spinning this way. As the planet spun this way, it's been kind of clumped up, swept up into a bunch of little chunks, which we call moons. Moons orbit planets, planets orbit sun. And we know that basic idea. So most moons were formed that way. If they're going the wrong way, it's a good guess they're captured, right? From where? From the asteroid belt and the comets. We're going to get to that. Okay. Let's talk about it. How many moons? Well, Mercury has none. Venus has none. We studied our moon, called Luna, or called Moon as a name. Mars has 2. The god of war. Why? Because it looks reddish, really orange. Really, it's a iron oxide. It's a rust. And so, kind of unfair to call it the god of war, but whatever. And so then you're going to name its moons after something that has to do with war, fear, panic, terror, dread, whatever. I don't expect people to memorize those names. Just get acquainted. We're going to get acquainted, and I'll tell you some things that I like you to memorize. And so we'll talk about these planets, these moons. Collision ejection. That's how we got ours. Mars got it captured. Captured a couple of asteroids. From where? My very excellent mother actually just sent us 9 pizzas. Asteroid belt, right there between Mars and Jupiter. So a couple of, and the way this works is that, when Moon, which was twice as wide, like the size of Mars, putting all the evidence together, that's the best solution to it. But when Moon slammed into us, it came back together in little bits, and there was enough stuff that it pulled together from all sides with gravity and kind of formed itself into a nice sphere. Not perfect sphere, but a nice sphere. Whereas if there's not enough big chunks, and not enough to pull from all sides into a nice sphere, you're going to get potatoes. And I'll show you those. So that's the idea. We're going to do an overview here in just a second. Okay. So to finish that thought, here we have a nice roundish, spherical, nearly spherical moon. Mars has those 2 little potatoes, much smaller, much closer, and we'll look at those. So take a look over here at the board, and we are going to look at our hood, right? You know our hood. My very excellent mother actually just sent us 9 pizzas and Cokes. We've done a lot of exploration, talked a little bit about that. And so right now, we're going to come in here and we're going to study, so I think I got 12 of the about 200 approximately, because we find more and I get tired of being wrong. I keep hedging my bets. Moons of our solar system. So we know that we look for planets around other stars. That's really hard to find. They're teeny tiny, and then moons, tiny, tiny. So it's hard, but we can imagine it. And so the best we can do right now is to study these guys. And make that a little better here. All right. So we're going to study these. And what are we going to study? So here's the 12, and we've got Moon, or Luna, for Earth. We've got Phobos and Deimos, which I'll show you really quickly, for Mars. And out of the 60 to 80, whatever, moons of Jupiter, we're going to study the 4 Galilean moons, Io, Europa, or Io. I'll use that as a memory aid, but Io, Europa, Ganymede, Callisto. Then we're going to do 3 of Saturn, Enceladus, Phoebe, and Titan, out of the 60 to 80, whatever moons that Saturn has, right? I've circled these as particularly interesting targets that people are working on sending missions back to. We'll see why. I'll mention Miranda over here around Uranus and more evidence of collision, kind of an interesting little thing, really quick, 10 seconds, I don't know. And then Triton, I'll mention too, also very quick. So trying not to be overwhelming there, but we'll talk about some of these details. Okay, what should you know? You should know this, that the biggest moons out of all these, we've got the three biggest, and they're about the size of Mercury, right? But they're not even close to Sun. They're way, way out there. And you know the distances. Make sure you keep remembering 10-4, big buddy, and all that. About the size of Mercury. What would that look like? This, right? And the next four biggest, including Moon, are moon-sized, about a quarter of the width. So I got Mercury size and Moon size, and the other one's smaller than that. Little bits, and smaller than this too. So little worlds, right? And so little, and they're way far out there. Come on, this is gonna be cold and dead, right? Those things are going to be cold and dead. Of course they, oops. Well, we can guess, but we aren't always right. Okay. Small, so we'd expect them to be cold and dead. Most are far from Sun. But, here's the key, and I'll come back to this, but I want to give you the main idea that I want you to take away from this is that the outer moons, although not very big and very far away, so cold, are composed of a flexible material. So if I try to flex a metal chunk, it doesn't flex very well. Rock can flex, not as much, but it does in our mantle. We talked about that some. And so two factors are key here. You've got a flexible material, and I'll show you a graphic. They get pulled from the other moons and from these large planets. They get pulled, and we get a tidal effect, creating kind of a kneading or a stretching and relaxing, creating a heating from friction. And it's a big deal that they're flexible. If it's ice, that's pretty darn. Take a snowball, you can go like that, right? Easy enough. So small, yes. Far away, yes, but not cold and dead. In fact, we've got this tidal heating, this flexible material, and solid ice can become liquid water. And we see worlds, and this is part of the key, where could there be life? Right. So not only do we develop technology that ends up in our hospitals and our pockets and whatever, our music, but we learned more about biology. We study this and we answer some more age-old questions. Are we the only life in the universe? Now you've seen there's about 100 billion galaxies, approximately, and about in each of those, on average, maybe 100 billion stars. And now with each star, some planets, that's since 1996 and on, found more and more of these planets, and at least in our neighborhood of the galaxy. And then we know around planets, naturally moons form. So all these opportunities for life. Are we the only life? We don't know. We don't know. We do know the odds are very great that there's life elsewhere. What kind of life? Simple life? Microbial life? Compassionate life? War-like life? I mean, what's it like? So we're looking for life, and this is the only place we can go. So it turns out, much to our surprise, as we get into the 1980 and beyond, these places might be places where we actually do find life. We're still searching for it to see, and we'll learn more about life that way. So let's talk about those Mars moons real quickly. Just give you a quick tour of them. And when you're done, hopefully, again, you'll enjoy looking up at the night sky. And go here. There we go. I love that picture. Love that picture. Okay. So, review. When you look at this stuff, think about it. 2 captured asteroids. I'm probably not the only one that calls it potatoes. I'm sure I've heard other people call them potatoes. Why? Because they look like potatoes. Look at them. They got hit too. You see the craters? But they're tiny. I don't expect people to memorize this, but 15 miles, just think, how far would you go from here to 15 miles? What would you go to? You know, where would you get to? Or 10 miles. This is 10 miles. So it's not very far, right? It's a quick drive, like 60 miles an hour. You 15-minute drive, a 10-minute drive. And they're actually very close to the surface. So this one orbits in 8 hours. Remember, Kepler's third law still applies. If it's closer, it's going to go faster and shorter distance, only 8 hours. This one's a little farther out, it takes 30 hours. But still, ours takes about 4 weeks, right, to go around. It takes 8 hours, like, oh, there it is, oh, there it is, oh, there it is. And the scary thing is, it's coming in, it's spiraling toward, it's going to crash in maybe 50 million years, so probably okay. We see a 6-mile wide crater, so going from here to here, where would that be a drive for you, going from your town to another town? So that's a sense of what these are, but to me, those look like potatoes. Let me show you this other one. And it really looks like potatoes here. And there's a lot you can study. So it's only 4,000 miles above our surface. I did this, I should redo this. Really, it's really 240,000 miles is a better kind of round off number. But I just thought it was easier to remember, but like 240,000 miles is really much closer. It doesn't matter though, right? Whatever. So it's much farther away, and our moon is spiraling away. I'd rather spiral away than spiral towards us, right? The way that this is. So just little bits, little bits. It's small, but it's close. So being close makes it look bigger. Being small makes it look, well, smaller. So we've got Mars rovers on the surface, and we've got Mars orbiters up there. A lot of spacecraft up there. Be surprised. Check that out. Looking up, not with a person, but Mars rover, you see a moon passing in front of the sun. Now, Mars is farther away, 1.5 AU from sun, so sun would look smaller. Are the moons big enough to block sun? No. This would be like a solar eclipse or a partial solar eclipse here. So that's just kind of cool, whatever. There they are. That's not that cold, 25 degrees Fahrenheit, depending on where you live, but it's not, but that's really cold, right? Out of the sunlight. All right, so those are our worlds. And so when we go to the outer planets, so that's where it's happening when it comes to moons. Lots and lots of moons, most formed in co-creation, basically ice and rock with water, ammonia, and methane, right? Rings are moon, if you got moons, you got rings, because they're litter bugs, right? So they can spew stuff out, or something can hit, and chunks go around, and they keep orbiting Jupiter, Saturn, Uranus, and Neptune. So lots of that. They're debris from asteroids and comet going around as it captured, okay? So that's basically, just keep it simple. That's what they are. They're all gonna have rings, but only one stands out, Saturn. And we didn't really know about the other rings till you go out there with Voyager and so on. And so you go, oh, there's rings here too. Well, that makes sense because they got lots of moons. They're gonna have moon litter, moon debris. And so, you know this. Do a quick review, pause, you know what it is. Ah, yes, Mercury sized. And I say the next 3 here, but the next 3 and our moon, so let's say the next 4 largest are moon size, including, if you include moon, right? And we went over this, so quick review. We expect them to be cold, dead rock. They're not that big. We know that those are cold and dead inside, and they're closer to sun. Now you get farther away, and that size, of course they're cold and dead, but you know the answer. You know the answer. Surprise. How can that be true? You know the answer. Tidal effect. And, let me add, and they're a flexible material. You do that, you can get warming from rubbing, right? to turn solid water into liquid water. So here's a nice image. And we're going to study these here in just a second. But if one of the moons gets a strong pull of gravity from this big old planet, right, and it gets tugged by other moons, and it's flexible, you could create some liquid, right? You can create some heat, you can create some gas. That stuff can be released through the surface. Volcanism, what? Let's study these guys in order now. So I have in the book, Memory 8, I got the names in order, the approximate widths, the time to orbit Jupiter, and special features and surprises, just a little bit. This is the most detail that we'll go into. But let's do this because these are for, you know Jupiter has a lot of moons, right? 60 to 80 moons. But these are the biggest four, and that's why Galileo, with his telescope, which he didn't have plastic, but you know, with his telescope, that's why Galileo could see them. And that's why with even binoculars, you can see them. But the naked eye, not quite good enough to see these. So we call them the Galilean moons, the biggest four. And there's something quite interesting about them. So my memory aid is this. Hey Jupiter, I owe your granny a call. Let's take a look at what that means. And then maybe I'll show you some pictures. All right, so here they are. So I've got a picture here of Jupiter with its bands, got its darker belts and whiter zones of clouds, white clouds forming as the gas rises, and the Eye of Zeus, so that's my name, or Great Red Spot, 2 Earths wide. And then I just line these worlds up, and we're going to talk about this in a second. So we know that they're flexible, and we have tidal warming, making them not cold and dead. Interesting for life. The memory aid is I owe your, Y-U-R, granny, a call. You can make up your own. Now, the real name is I-O, or as a Latin-based language, it should be E-O. But people do say I-O, so, and that's the memory aid I got. But I do like saying E-O. Anyway, I-O, your, Europa, granny, or Ganny, no R, Ganymede, it's one word, Ganymede, a call, or Callisto. That's what, if you line them up, that's their names. Now, you might look at the mythology, the Greek mythology. It's kind of interesting, a little racy, a little interesting twist in there too. But but that's just again one person's. Hold on, sorry. I have to redo that. One person's, not one person, one people's, right? The Greek mythology. People around the globe, there's other people, that have been around, looking up, making up their stories. So there's no meaning here. It's just connected to stories. It's just storytelling, right? So anyway, you know that. How wide are they? Well, these are the smaller ones, about moon size, about a quarter of the diameter of Earth. And these are the bigger ones, Mercury-sized, about a third of the diameter of Earth, right? So, the big ones and the two small ones. All right, and other ones after that, just little bits of chunks, and even smaller than that. Okay, so what's interesting? Galileo saw these. That's why they're the Galilean moons, right? And here's what's cool. How did he know? He just saw them as little twinkles, right? How did he know they weren't stars? Because they orbit rapidly. So you look one day, Eo's over here. You look the next day, Eo's over here. You look the next day, Eo's back over here. Approximately, Eo orbits in 2 days. And I like patterns that I can remember to get a sense of. Europa orbits times 2, 4 days, times 2, 8 days, about a week, times 2, about 2 weeks, 16 days. It's pretty close. Checkmate. So what does that mean? That means that every day you look, they can be changing. You could have 1 over here and 3 over here. You could have 2 and 2. You could have 3 and 1. You could have 4. Or you could have one that's behind Jupiter or one that's in front of it and you only see 3. But you see it changing rapidly as long as it's out during nighttime. Okay? So what's so interesting about these? I'm going to tell you that Ganymede is the biggest moon, but similar size here, but biggest moon. That's its special feature. I'm going to skip this, leave that to your exploration if you want. I'm going to tell you, and then I'll show you pictures, that Io has active volcanism. I'll show you a picture. Yeah. And then Europa, the one place here that sounds like a place you might think of on Earth. Does it have life? We don't know. We want to go. And remember, I boxed it in over there. That is a candidate for life. Why does it have possibly life? I'm going to change this a little bit. And I'm going to go, all right. The reason is this. Europa has an interesting composition, it seems. And we need to go explore more. We need to go back. See, we think there's kind of like the terrestrial orbs. There's some metal in the middle. You can look and see what the current thinking of how wide it is and stuff. Don't trust my drawing here. I just kind of sketched it. With rock, right? But rock has minerals, and minerals are important for life, as is minerals and water. And so what we have here, beneath that surface, is liquid water. Liquid water. We seem to see a lot of brine water, like salty water. Hey, our oceans, right? And so there seems to be this liquid water there. And the surface, though, is hard. It's solid. It's got a solid surface of water ice. Now, the surface is not smooth. It's actually quite jagged. And in some places, it's thinner. So what do we want to do? We want to go in. In fact, the Galileo mission, the first mission to go up and orbit one of these big buddies, right? Left in '89, right? Took, 5 years to get up there, and settled into orbit. Right? And when it was done in 2003, check my numbers. Yeah. So when it was done, do we just let it go adrift? No, it might hit here. What's wrong with hitting here? You might contaminate it. We want to know whether life started somewhere else and was sustained, was supported. The development of life. So you don't want So what do you do with Galileo? You know this. We just send it into Jupiter. Took data as it went in. You see how small Earth is compared to Jupiter, a little tiny thing like that. We see we take measurements, temperature, pressure, wind speed, chemical composition, whatever you got, so that we don't hit Europa. It's not that we don't want to go there. We want to go there, but you've got to sterilize it. And it's amazing where life can live on Earth. It's in places that are like battery acid, and it's amazing how life can sort of sustain on these trips. We weren't sure that Galileo didn't have some microorganisms that were functional there, right, or something. So somehow sterilize it. I don't know, UV light. I don't know what, right? So then you want to look for maybe a place that's less thick, and it'd be nice if you could burrow down in there, maybe roll around, but it's really quite rough underneath that. We know that from going to the ice sheets of the Arctic and so on. It's rough underneath these nice smooth sheets of water on the top, ice on the top, but rough on the bottom. So anyway, you gotta go down there, roll around, have a little camera, check things out, measure things, see if you can get some microorganisms. That's a lot of complex science and technology, right? But we're pretty far along, aren't we? So this is being planned. We got the European Space Agency, ESA. We've got NASA. We got people working on this. So maybe you've got that. But maybe there's fish. Maybe in the year about 2000, biology had a branch called astrobiology. Like, well, how would life develop in other environments? Small gravity, so you wouldn't need much of a backbone, would you, in the water? Maybe you're going to have astro squid, space calamari. Maybe when we go in there, that big old squid's going to eat it up. I don't know. We don't know, right? We don't know what's in there. So that's exciting. Missions being planned, and when it happens, you'll know what's up with that. Those are the Galilean moons. Let me take a trip through Enceladus, Phoebe, and Titan of Saturn. Quick on Miranda and Triton. And that's what I got for moons. And very, very interesting places. And of course, you can explore more. Let's do this. That's better. All right. And so, Io, quick review, always review, Io, or Eo, Europa, Granny, Ganymede, Call, Callisto, Io, Granny, Call. And this is what Galileo sketched. And you can see it because they go around, right? Eo 2 days. Io, Europa 4 days. Io, your Granny, Ganymede, 4 times 2, 8. Io, your Granny, a call, Callisto, 8 times 2, 16. So they're going to be changing, and he just saw them as dots. Otherwise, you'd think they were just stars, but they're changing so rapidly, he could see them. But we, of course, have better equipment. With a good telescope, you can see this, you can see bands. And, of course, you see them change. They can change position, 2 and 2, 3. Or sometimes you only see 3 because one's in front of or behind. But if you go there, you can study them. And so these worlds, these planets that were dots in the sky, we've come to know as worlds, as having features and characteristics and processes. And now we've come to know that the moons do too, in a surprising way. So our intuition, sometimes we're surprised. Here they are. I owe you, Granny, a call. Active volcanism. Water ocean underneath, maybe life. The biggest moon, leaving this then, that's the Death Star. It sure looks like it, right? I'll leave that to you. So, here's Io. Jupiter, not a solid surface. Crazy. We colorize, you can see the shadow of Io. When Voyager went by, capturing this image, and there's an astronomer that was analyzing this image. I believe this is right, and she's interviewed sometimes and expressing this reliving that excitement and going, oh my gosh, I'm the first person to see at least a photograph of, like, what is that? A moon? What's that bump? What is? It's a volcano, volcanism on another world. We've never seen before on a moon, our size, a moon way out there in the cold. Then what do? Well, we go back and take better pictures, right? With Galileo mission, right? And we see this sulfury, interesting, not lava volcanism, but heating up and spewing out all over the place, really cool. Active volcanism for Io. Europa, having this kind of a metal and rock and some thickness of water. I know I kind of exaggerated over that, but rough surface, and we want to go down in there to see if there could be life. So that's up there. What's up there? Ganymede, Callisto. All right. You know that they aren't the only moons, but they're the ones that we focused on. Jupiter, if you got moons, you got rings, you got moon litter. What are you going to do? Cassini passed by, so they set it up. You didn't have to, but you might as well pass by somewhere. If you're coming from the East Coast to West Coast, you might as well go through the Rockies, right? It's beautiful, or Grand Canyon, somewhere cool. So passed by Jupiter on its way to Saturn, left Earth in 1997. So just to get a sense, you can't memorize all this unless you do it over and over. And there's our beautiful Saturn, and we know that as you get up close to those rings, that they're related to the moons as well. Moons can sweep up accretions, sweep up gaps in the rings, the divisions of the gaps in the rings. And they're little, as it turns out, over here, they're chunks, maybe as big as a baseball, basketball, house, car. Some as big as that, I think, and rock with snow and snow, ice. What is it? It's water ice, like a lot of chunks there. Have a snowball, and they're thin. What's amazing is flat and thin, and we know that those chunks can actually sweep up and form a moon, or moons can throw off stuff and become rings. So there's that interplay that you should know. Of course, these are most dramatic. Cassini, the Cassini mission was named after the Italian astronomer Cassini, who came after Galileo, so telescopes has gotten better, good enough that he could see that little gap, which is called the Cassini division. Come to find out, there's lots of divisions in there, and we study that, and we see these moons, and what do I want to talk about? Enceladus, Titan, and a teeny moon called Phoebe. The rings, so thin, moons sweeping up the debris or shepherding, creating gaps and so on. A mile thick, really thinner. I mean, think a 2-story house thick. So very thin. Lots of moons. And so this is a great picture. We have our moon, Mars, 2 tiny things, you can't even see them. Asteroids can have chunks orbiting them because everything has gravity. Here's just 4 of the 4 biggest moons of Jupiter, Io, Uranus, and Paul. We know there's lots of other ones, but these are Galilean moons. For Saturn, we're going to go Enceladus, Phoebe, teeny tiny Phoebe, surprisingly interesting, and Titan. What do you notice about Titan? Miranda real quick, and Triton real quick. This is an old image. I like to keep it because for the longest time, and I won't throw out too many numbers, but this was the only moon of Pluto. That's kind of a fun mythology. I mentioned it in the book a little bit, just for fun. And then, they found 2 more. And then when I was writing the first edition of that book, I found 2 more, so I made a mistake. So now it's got 5. What will we discover? Life, whatever. We'll see. Enceladus makes me hungry because it does make me think of enchiladas and enchiladas. There you go. What's up with it? It's tiny, 300 miles across, way out there. Crazy, right? Just go to NASA for these pictures. 300 miles, you can drive that. It's a 5-hour drive at 60 miles an hour. But it's sending out plumes. You see, with Europa, you had to go in. Now that you understand that, I had to go into Europa to find life. Maybe I can just fly through that. Why would I want to fly through it? Because it's got water, carbon dioxide, ammonia, ingredients for life. But it's cold and dead, isn't it? No. Why does it have the plumes? Why does it have the plumes? You know why. Because it's flexible and it's pulled from all sides. So this is missions being planned to go there. Now Cassini went through and passed and so found this out, but wasn't designed to kind of go through at the right height and gathering and having a wet lab on board to analyze it and see if there's any organisms, any life created. It's interesting. We'll see what we learn. So Enceladus is a hot topic when we look for life in our hood. Lots of chunks of ice out there, right? As it cools, it cracks. One of my favorite pictures, look at this, amazing. You don't have to memorize all these things. How gorgeous is that? The thin rings and the gas whipping around, incredible speeds, and astronomy. It's just a wild world out there. And then those little teeny tiny Phoebe that was captured, a captured moon. So it's good for that. Clearly got hit. You can see the surface doesn't have an atmosphere, right? I mean, couldn't, right? Certainly not active. Wait a minute. It's actually spitting out some gas, maybe warm from the tidal heating. So it's more interesting than you would expect. I just thought I'd mention it, and it's a captured comet, right? As it were, or a Kuiper Belt object. So let's go here. We've done two. We did Enceladus and Phoebe, real quick. Just interesting that they're spewing out gas. What's going on? Could there be life? And then Titan. Interesting thing about Titan, when you go past it the first time and you go, oh, wait a minute, what was that? I can't see the surface. What was that? I can't see the surface. What is this? Now I like this, and if I need to, Calvin Hamilton, thank you for this picture, 1999. At that time, we had not gone past Pluto, and that's the best we had seen it until 2015. A 9-year trip, 2006 to 2015, of New Horizons traveling like 36,000 miles an hour out to the farthest reaches, past all this stuff. Better images. Now, we're looking at moons, and we've got 3 that are Mercury size. That's not a moon, but to get a reference, right? And then we've got 1, 2, 3, 4 that are moon size, and then Pluto's smaller. So I'll give you a hint at chapter 9. So interesting worlds, but Titan's the only one you can't see the surface. So we go. And so when, don't do that. All right. So when we're going out there on the Cassini mission, ESA, European Space Agency, said, hey, can we hitch a ride? We got this craft. We'll name it after this physicist Huygens, Huygens, and drop it down and see what we see. What could be there? What could be there? So you can see this, and I'll show you a little clip of it. Orbiting Saturn. It's the most world-like kind of place we've seen. Right? It's got riverbeds with flow patterns, pebbles, lakes filled with liquid, erosion from wind, liquid flow, sand dunes, tectonics, mountains, ridges, ski resorts, volcanism, outgassing, right? Outgassing, atmosphere, second densest next to Venus. Remember what Venus looked like? So now you piece these together and you actually know of a world that's really exciting right now. But its cycle goes in a methane cycle. It's got clouds, it's got rains, it's got weather, it's got seasons, but methane, not water. Water is oxygen with hydrogen. Methane is carbon with hydrogen. We talked a little bit about diamonds. It's got all this stuff, and they found unicorns and rainbows and Okay, they didn't find that, but we want to go back and see if any life can live in a methane cycle. It's so far out that water would be frozen, unless maybe it's under the surface too. Lakes of liquid methane. What's methane? It's natural gas. Natural gas is almost all methane. So that natural gas that you turn on the stove, whatever, so cold it turns liquid. Right? So it's an interesting cycle. It's an interesting place. Let me show that to you a little bit. I'm going to go here and pull this up. go here. I don't know who that is. Over here. And I'm going to go fast forward through. So, talking through. You can look this up. NASA. Going through the atmosphere now. Go fast. Through the atmosphere, you start seeing mountains. But the mountains aren't very tall. Maybe I'll let you look that up. You know, kind of just hills at best. Like, not much. But we'll explore it. Grooves and channels. And then this probe, European Space Agency probe, ESA, gets closer to the surface. And this is kind of cool. These are like baseball-sized chunks of water ice because it's so cold, it's solid. And then you see, oh, look at the shadow. The shadow of the parachute because it has an atmosphere. So the probe came down with a parachute and you saw that shadow coming. So this size, that is like baseball size and it's up close. And again, we look for water. So we've got questions. We want to go back, but this was pretty crazy world. And there you've got Titan. Now we go to Uranus, and it's got names. They decided to name them after Shakespearean characters, whatever. You know that Uranus is tilted over. Here we go, Miranda. I want to talk about then Triton there. So Miranda is pretty cool. You could just, again, Google the images or whatever. You can get this from NASA. So you got these images, and we know that moon smashed into us, broke into a bunch of little pieces, ended up half as wide, came together into a sphere. We know that asteroids are kind of like potatoes. What time is it getting late? And this guy looked like he got slammed into big pieces and maybe came back into different places, settled in. Some people call it the Frankenstein moon. I actually like to call it the Picasso moon because if you look at his, let me draw the nose over here and the eye over here and mix it up. And Picasso was a brilliant painter even when he was young, but then he started getting interesting. So again, evidence of collision. And to finish this off, Neptune has captured a comet. Where are we? Has a captured comet of Triton. I can let you look at that. There we go. Quick little summary. We're on to the leftovers. This is the last bit of our solar system. It turns out these are very important. And in fact, we know high impact collisions might spark life, creating amino acids if there's an environment to take for that off. We know that there are processes that we study. We know that these can take life, but they can perhaps give life. Who knows? Let's study the leftovers in chapter 9. Cheers.